So in today's video, we will be seeing few topological constructions. Most of you might already have seen these constructions. So you can check in the description what all constructions we would be seeing here. And if you're familiar, you can skip it. And okay, yeah, so let's start. For the first one, we have quotient spaces. So we all know that if we have a topological space and if we have a subset, we can always take its quotient. So now let's just see formally what it means, that if you have a subset A of a topological space X, then X mod A is a topological space in which you consider this A to be shrink to just a single point. So this quotient map is then sending every point X to its equivalence class here. And now then every point of X which is in A goes to the same point, whereas every point which is outside of A, that is in the A complement, is going to an equivalence class which has just one element, that element itself. Okay, so this way we have the quotient map defined here. And here we are seeing it in the sense of one set, but this can actually be done with a family. Okay, because when we are dealing with, let's say, more constructions, when we will see later in this video, we would be doing several sorts of shrinking at the same time. See, here we said that A is being shrinked to a point. There might be several A's which are being shrinked to different points. And that's why let's see what is the general way of defining this. So what you do is, if let's say this calligraphic A is a family of disjoint subsets of X, of course you want disjoint, otherwise this equivalence classes will not remain well defined. Okay, so what we say is that if you have so J is an indexing set here, and I say that for such an indexing set, if you collect some disjoint subsets of X, then we can define the quotienting business on each of the AIs, which means all the points of AI are being sent to one class. So I identify all the points of same AI. Okay, so X is going to be equivalent to Y if either X is same as Y, or for some I in the indexing set, AI contains both of these. Okay, and for such a quotient, we would write X modulo the family A. Okay, so generally this A, when you have more than one sets in the indexed, like when J has cardinality more than one, we simply write A by the symbol tilde instead of writing it as any family. So that is just a bookkeeping, but let's move forward. So notice that if my cardinality of J is 1, which means there is just one set in this family, then this is nothing but the usual definition of the quotient which we have seen earlier. Okay, so this X modulo calligraphic A becomes the X modulo A for some A, which is this exactly the A which we would have here. Okay, few basic examples that if you have taken closed interval 0, 1 and you mod it out with the set 0, 1. Okay, so this is one set, right? It has two elements, one set, and both of these elements are being identified with each other. It's like taking an interval and joining the two endpoints. So you get an S1, right? Further, if I put it in the notations, I see that 0, 1 is same as B1, and this 2-point set 0, 1 is its boundary, right? And so this S1 is nothing but the B1 modulo boundary of B1. Is it also true that if you take Bn, the n-dimensional ball, and you consider its boundary, the Sn minus 1, the Bn modulo that particular Sn minus 1 is going to give you Sn. Just check for yourself. And some pictorial presentations, if you want to see, we will start with a rectangle. Let's assume there is a rectangle here. Okay, and you identify opposite edges in the same direction. Then what you get is a cylinder. This entire line comes and attaches itself here. So you have a standing cylinder here. If in this itself you further identify the two circles which are created at the top and the bottom of this cylinder, what you get is torus, right? And this is happening when you're identifying them in the same direction. But if you invert the directions and then you identify, which means this point gets identified with this point here somewhere will be identified with this point here, and so on, then what you get is a Klein bottle. Okay, whereas in this you were identifying this point with this point, this point with this point, and so on. Also here itself also you can see here, to make the cylinder, I first did the identification of this along this in the same direction. Had I done the identification of this line with this line in the opposite direction, which means a point here would have been identified with a point here, then I would have gotten a Mobius strip, right? And then if I identify the boundary of that Mobius strip with itself, I am going to get the Klein bottle again, which is same as saying that whether you do this identification first, then this, or first this and then this, it does not make a difference. So either you come from the cylinder and twist the other edges, or you take the Mobius strip and attach the edges in a nice way. Both ways are going to give you the Klein bottle. Okay, this also means that whether in this indexing set, if AI is, which AI shrinks first does not really make a difference. You just shrink them. Okay, after this, let's see what sum and wedges of spaces are. So sum is nothing but the disjoint union of spaces, and then any subset will be open if it was, so of course it's a disjoint union, so the open sets of the two spaces also comes through this disjoint union. So then a set in this collection is going to look like U disjoint union V, with U coming from X and V coming from Y. Then you say that U disjoint V is open if and only if U was open in X and V was open in Y. Okay. And the next concept is about the wedge of spaces. So if we want to look at the wedges, first thing to keep in mind is that this is done through based spaces. Okay, what does that mean? That means that in a space, you identify a point and consider that point as special in some sense, like how we used to do when we defined fundamental group of spaces. So you take two base spaces x, x naught. So this x naught is the special point for the space x. Y has a special point y naught. Then the x, x naught wedge y, y naught is the space which is being obtained by taking disjoint union of x and y and identifying the points x naught from x with y naught from y. Okay, so this is precisely what you would want to see. Let's say if you have two circles and since circle, so all the path connected spaces, which point you are using does not really make a difference. So if you choose any particular point and you take their wedge, what you get is a figure 8 space. Okay. Now we come to the very important definition which is there in topology, and that is of homotopy extension property. So Everyone knows what a homotopy is, okay? And now we are asking for homotopy extension property. So far we have always seen things like extending a map, extending a homeomorphism, etc. Now we are trying to extend a homotopy itself. Recall that homotopy is a collection of continuous maps, right? It's not just a continuous map from some space x to y. It's a continuous map from x times I to y, and it is continuous for every t in that I. Okay, so what it asks or demand is that if, let's say, you have a topological space x and a subspace x, a of x, and you have a map defined from, so let's first consider the x cross I. So x cross I is going to be this big box, right? If x is this horizontal line, this full horizontal line, and A is this some portion of it, A is a subspace. So then A cross 0, 1 is going to be this box here, correct? And X cross I, which is 0, 1 is going to be this full box. So what it demands is that if, let's say, given a topological space Z, you have map from this entire piece to Z and this entire piece to Z, which means A cross 0, 1 to Z, you have the map, and X cross 0. So this horizontal line is X cross 0, the 0th cross section. If you have maps from both these spaces such that the map which is defined here agrees with the map which is defined here on this piece. So A cross 0 is something which is common in A cross 0, 1 as well as X cross 0. So if you have a map, if you have maps which are defined from this filled rectangle as well as this horizontal line that agree on A cross 0, one must have a map defined from this whole of rectangular piece, which is going to respect this particular map as well as this map. Okay, that is why you're sort of saying that you extend the map on this to whole of this, and not just that, you are extending the homotopy which was given on A. Having a map from A cross 0, 1 to some space is same as saying that you are having a homotopy from A to that space. So you are extending that homotopy of A cross 0, 1 to Z to a homotopy from X cross 0, 1 to Z. Okay, so if I put it in a commutative diagram, what I'm really asking is that A cross 0 naturally sits inside X cross 0. You just take the inclusion. So any A comma 0 goes to A comma 0, and then A comma 0 sits inside A cross 0, 1 via the 0th projection. So any A comma 0 goes to A comma 0. Similarly, X comma 0 will go to X comma 0. And this map is given to us, which is the filled rectangle, which is this piece where it agrees upon. So you are given this map G, okay, you're given this map F bar, which is extending this F. We are asking that this map should exist. Okay, so this is a map which extends this map as well as this map. And that is the case when this is going to be commutative. Okay, so homotopy extension property for a pair x comma a means extending the map G to G bar such that G agrees with F bar. Okay, and as I've already said that it's called homotopy extension property because you're really trying to extend a homotopy. And this should be true for any topological space Z. So if at all you have a structure like this, you have a commutative diagram which fits this picture for any topological space with these maps. If I am saying that the pair has a homotopy extension property, this map exists. Okay. Now, a small exercise for you is that to check if X is geometric realization of a finite dimensional simplicial complex and A is the geometric realization of some subcomplex of it, then this pair XA has homotopy extension property. So HEP is shorthand for homotopy extension property. Okay. Now we come to one of the most important propositions which is used in topology very often, like really, really often, is that if you are starting with a simplicial complex, okay, and if you look at some part of the simplicial complex, which is some subcomplex of it, which is contractible, then if you mod out the space by this subcomplex, then you are not losing anything. What it means mathematically is that if X is a polyhedron of some simplicial complex K, A is a polyhedron of some subcomplex of K, okay, then if A is contractible, X mod A is same as X up to homotopy, which means you can safely get rid of A, and this does not change anything up to homotopy. This is something which is needed very frequently in topology, and we'll see in some time. Okay, so to see a proof, obviously we have the map Q, the quotient map from X to X mod A, and since we know that A is contractible, we know that there is a homotopy from a constant map on A to the identity map of A. Okay, let FT be this homotopy. Okay, so this is the other way around from the, doesn't make a difference, but just for the sake of fuzziness. So FT is a homotopy from the identity. So one subscript A means identity map of A. It's a homotopy from the identity map on A to a constant map on A. Okay. Now we draw this diagram here. Is this better visible? So from A cross 0 to X cross 0, you have these obvious maps here all across. Outside maps are always obvious. Okay. And A cross 0, 1 to X cross 0, 1 is taking any A comma T to A comma T itself. The inside maps are the important ones. So this map is nothing but the identity map, which you have said here, because what we are saying is that FT is the homotopy from A to X. Yeah, it's from A to A and A is sitting inside X. So you can consider all these FTs to be from A to X. Okay, so this is sending any A comma T to FT of A, and now F0 of A has to be the identity map, and F0 of A has to agree with this map, which means this map I am going to take as the identity map. So A comma 0 goes to A. Now take its obvious extension. So you send any X comma 0 to X. So inside map I have considered as X itself. Okay. So I have this continuous map, I have this continuous map. All these maps that are there in this picture are continuous. And just check that if you're taking A comma 0, like this particular triangle is commutative, sends any A comma 0 to A comma 0, which comes to FT of A, and A comma 0, which means F0 of A, which means A, okay, and A comma 0 comes to A. In this diagram, it's anyway commutative. These are all inclusion maps. So what you are saying is that this, excuse me, This is a commutative square which has maps from a cross 0, 1 to x and x cross 0 to x. And since x and a both are simplicial complexes, a is a subcomplex of x, as in a and x both are polyhedrons of simplicial complexes. By this exercise which I have assigned here, we see that the pair XA has homotopy extension property. Therefore, there exists a map FT from x cross 0, 1 to x, which is going to extend this map and at the same time going to extend this map. So extending this map means what? That on A, at 0th time, it is extending this, okay, and for the later piece it is extending this. So f0 is the identity on x by assumption itself. If it has to extend this map, then f0 has to be this map, which is the identity on x, okay, and we wanted that f at later it should remain should remain as a constant map on A, okay, at the time 1. So f1 restricted to A is going to extend this particular piece, which by assumption is a constant map on A. So we have a homotopy which extends these, and now this along with these compositions gives you the desired result. And these homotopy extension properties are really useful because many a times in topology, when you're trying to prove homotopy equivalences of two spaces, you have to sort of fatten up one particular space so that these calculations can be carried out. So just how sometimes cylinder is not sufficient and you just an S1 is not sufficient and you have to create a cylinder over it. Same way you have to fatten up things. You will see when more things of this type come in future. Now we move to joins and products. So products are not really very interesting, but just for the sake, let's just see. So Cartesian product of two spaces x and y has as the point set x comma y with x and x, y and y, the usual Cartesian product of two sets. And its topology, the topology of the Cartesian product of x cross y is generated by open rectangles. So here in this, when you have u cross v with u subset of x, v subset of y, whenever both of these are open, the u cross v is an open set, and now the topology is generated by such open rectangles. So that's the topology on x cross y. However, if you see, let's say you like very simple topological spaces are simplicial complexes. If you take two simplicial complexes, rather just takes one simplices. So it's a one simplex, this is a one simplex. Then their Cartesian product is going to have this structure, right? But this is not even a simplicial complex. You will have to triangulate it to make it into a simplicial complex. So this is not something really desirable. So that's why there is another concept called joins. Okay. And for join, we see the join of two simplicial complexes is a simplicial complex. So let's see what is the definition. So if K and L are two simplicial complexes, then the vertex set of this, so this asterisk is denoting the join operation. So vertex set of K star L is the vertex set of K with a ordered disjoint union taken along with vertex set of L. What does the ordered disjoint union means? It means that you make a note of which element comes first and which one comes later. This precisely means that if you have taken two sets A and B, then their ordered disjoint union is defined as A comma 1. So all the elements of A are written as A comma 1. All the elements of B are written as B comma 2. Since A was the first element in this disjoint union, that's why A comma 1. B was the second element, therefore B comma 2. If there was another, it would have been a, let's say a set C, it would have been a C comma 3. And then you take their union. So a very striking fact is that, so in disjoint unions, we know that A disjoint B is same as B disjoint A. But for ordered disjoint unions, if you change the ordering, it does not give you same spaces, right? They are not equal. Of course, you will get same spaces as we'll see later, but they are not same. Whereas disjoint unions gives you exactly same items. And in this collection, a subset of this is going to form a simplex if the respective ones are coming from the K and L. Okay, so F ordered disjoint G is going to form a simplex if F is in K and G is in L. So for example, if you take any K to, like, let's say K to be one simplex AB and L to be one simplex XY, we are just trying to contrast it with what we took here. Okay. So clearly the vertex set of K star L is going to be A comma 1, B comma 1, X comma 2, Y comma 2, right? Because I have written K first and L later. And simplices are, you take one simplex of this, all simplices of this, and so on, right? And if you want to see the maximal simplices of a join are the products, or rather these sets with F and G maximal, correct? So since this has only one maximal simplex, this also has only one maximal simplex. So the maximal simplex of K star L is going to be given by A comma 1, B comma 1, X comma 2, Y comma 2, which forms a tetrahedron, right? So this is the simplicial complex which is obtained by taking join of these two simplicial complexes. Okay, so clearly this has a copy of K and a copy of L, right? Here this was a very small simplex, so you, like, it's easy to see, but once the simplicial complex is not just a simplex, these things become little tedious to observe. But yeah, clearly enough, the operation is associative. Sorry, this is a type. And hence, we can, so if let's say you have K1, K2, K3, we took three simplicial complexes, K1 star K2, and then taken join with K3 will be same as K1 taken join with K2 join K3. And therefore, for a simplicial complex K, we can define an n-fold join. So the n-fold join of K is defined to be K join K n times, where the simplices are actually F1 ordered disjoint, F2 ordered disjoint, and so on up till ordered disjoint Fn, where each of these Fi's are coming from K itself, right? So again, a quick computation for this n-fold join. If let's say D2 be a simplicial complex with two discrete points, 1 and 2, Then the geometry realization of D2, okay, this is a typo, it's a D2 here. This is isomorphic to S0, right? Just 2 points, disjoint points. And now these vertex set you can write as 2 cross n, because I've taken the numbers to be 1 and 2. So an element here will be 1 comma 1, 2 comma 1. Element here is going to be 1 comma 2, 2 comma 2, and so on. So that's exactly the set 2 cross n. And a subset of this is a simplex if and only if 1i and 2i does not belong to it, right? Because if 1i and 2i belongs to this set, this cannot be a simplex because 1 comma 2 is not a simplex, right? 1 is a disjoint point, 2 is a disjoint point. So recall the entire structure which we had for cross polytope, that you define the vertex set to be the set n union set minus n square brackets, and then a subset is going to form a simplex if it does not contain a pair of antibodal points. So if you consider this 1 as in some sense an antipodal point for 2, or rather name this 2 with minus 1, okay, they are going to give you isomorphic points, and here then it will be 1 comma minus 1 with cross n. So if you take the multiplication, mathematical multiplication, you will have points like n minus n, all these points, right? Starting from minus n going up till n excluding 0, and then you're saying exactly the same thing, that for no I and minus I both should be there. So this is exactly the structure here as well. Therefore this is same as the boundary of n dimensional cross polytope which we studied 2-3 lectures back. So this is nothing but the diamond n minus 1, but we know that this diamond n gives a triangulation for Sn, so diamond n minus 1 is giving a triangulation for Sn minus 1. Yeah. Now, another good property about join is that it preserves the homotopy type. What does that mean? That if you have two simplicial complexes whose geometry realizations are homeomorphic, okay, then taking their joins gives homeomorphic spaces. Okay, but so far we do not even know what a join of space means. So let's just see that first. So if you have topological spaces x and y, their join is defined as the x cross y cross unit interval 0, 1 with the equivalence relation, quotiented with the equivalence relation that at 0th level, so x cross y, if you consider that as one entity, then at the 0th level, you identify all the points of x to 1 point. Okay, so for every x prime in x, xy0 becomes same as x prime y0. And at the 1th entry, 1th level, you identify all the points of y. Okay, so if let's say you have taken x and y both to be the unit interval, then this is a cube, correct? X cross y cross 0, 1. This is a I cross I cross I. It's a three-dimensional cube modded out with this. So draw in your copy and see that this again gives you a tetrahedron. When the on one of the edges you squeeze entire edge to make it a point, on the other one you squeeze another edge along for this particular relation and get a point, and this way we get a tetrahedron. So this is it for the today's talk. And in the next lecture, we'll see some more constructions like cones, suspensions, and a few more. And what I have promised you here about this result we will see in the next class. Okay.